So this last unit is all about right triangles. And in fact, what we'll see towards the end of the period is that trigonometry itself is all about similar right triangles. Okay? We just talked about similarity, and trigonometry is based on similar right triangles. Now, when you guys looked at the Pythagorean theorem, do you guys remember what that was? What's the formula? Yeah. A squared plus b squared equals c squared. How many people does that ring a bell for? A squared plus b squared equals c squared. A few of you. Awesome. Okay, we'll review it today briefly, so if it doesn't, that's okay. That also has to do with right triangles. Okay, we can use the Pythagorean theorem to calculate a side length of a right triangle. Trigonometry also is a tool that we use to find out information about right triangles. So we are actually going to use those tools hand in hand in this unit, because they are both sort of tools in our toolbox that can be applied to solving any sort of problem that involves a right triangle. So today we're going to start off by reviewing the Pythagorean theorem, and then we're going to start to investigate this big word called trigonometry, which is not as scary as it sounds. Okay. Before we do that, though, I want to talk a little bit about how in mathematics we label triangles. So you guys should be writing this down. And there's two different scenarios that you could have when you have a triangle. One scenario is you have like a standalone triangle. Okay, so a standalone triangle is one that's all by itself. Oops, maybe something like that. Okay, it's separated from anything else. It's not attached to anything. And when we have this type of scenario, we can label the angles, or the vertices, the corners, with capital letters. A, B, C. You can use whatever letters you want. X, Y, Z, P, Q, R, whatever you want. So the angles are capital letters. Angle A, angle B, angle C. Okay. And then the sides opposite each angle. So when I mean opposite, I mean like across from the angle. So if this is angle A down here, and you go across from angle A, that would be this side over here, is labeled with the same lowercase letter. Okay? So here is angle A. This is side A. What would you call this side at the bottom? Yeah. Okay, so it could be called, okay, so you're getting into almost like a Pythagorean theorem thing with a leg, because it's at the bottom. So we'll get to that later, but just based on this rule, the side opposite each angle uses the lowercase letter. So this side down here, which angle is it opposite? B, yes. So this is going to get lowercase b. Okay? And then finally, the one sort of on the left side that's slanted is lowercase c. Okay? So that's one scenario that you could have. But the other scenario is when you have connected triangles. And then this method kind of breaks down. Okay, so let's say I have a picture that looks maybe something like this. Okay, so, and these points are, I'll call them D, E, F, and G. Okay, Now, if I wanted to talk about angle G and just use one letter for angle G, what's the problem there? Why can't I do that with the connected triangle, but I can do that with the standalone one? If I wanted to talk about angle G. Here's the point G. How many angles come together at that point? 3, yes. I saw some of you put 2 up. So I can see 2. One of them's here, this small one, and one of them's here, this even smaller one. But then there's the entire angle as well. So that's a third one. So there's actually 3 angles at that point. So if I just wanted to talk about angle G, you wouldn't actually know which of those 3 you were talking about, you were referring to. So this system where we just use one letter to talk about an angle kind of falls apart because now there's ambiguity, right? It's ambiguous around which angle are we talking about, okay? So what we have to do instead is for angles, we have to use 3 letters. Where the middle letter is at the vertex. Okay, so what I mean by that is vertex is like the corner of the angle. Okay, so if I wanted to talk, let's say, about this angle right here. Okay, the corner is right here, this point G. So to use 3 letters, I would just say, okay, well, where's it starting? D, G, E. So this angle, I could call it angle D, G, E. Okay? I could also call it, though, if I wanted to, instead of D, E, G, I could start at E and call it E, G, D. Okay, so you can switch around the 2 outer letters, the orders of those, but the middle one has to be where the angle is located at that point. Okay, how would you name this angle? What would this one over here be called? Yeah. No? Yeah? G, E, F. Yeah, and if you imagine drawing it, G, E, F, and just drag your pen over the path of the angle, think about the letter where you start, G, and then you go to E, and then you go to F, and that's the same way that you would name it. Okay? The other thing that you could do, though, is you could start it on the right side, and you could start at F, and then go to E, and then go to G. And you can also name it that way. Or angle F, E, G. Okay? Still the same angle. Okay, so that's how we name angles. For sides, the system that we talked about with the standalone triangle also breaks down. Because let's say, for example, I wanted to talk about side little d, lowercase d. Well, there are actually 2 sides opposite this angle over here, angle D. There's this one, and there's this one. So it's ambiguous as to which one you would be talking about. So instead of using lowercase letters, we have to use the 2 uppercase letters that connect the 2 sides together. Okay, so we need to use 2 uppercase or capital letters. Okay, so for example, if I was looking at this side over here, I would call it D, E. Or if I was looking at this side over here, what would this one be called? This one. GF. Okay? Questions with that? Okay, because I will be referring to angles when they're connected this way, or I'll be referring to sides this way as well, so you need to know kind of what I'm talking about. And this is standard practice in mathematics. All right, now let's actually get into some Pythagoras. Okay, so Pythagorean theorem. What type of triangles can we use? Oh, you have a question? Yeah, quickly. What type of triangles does the Pythagorean theorem apply to? Can we use it for any type of triangle? For whatever triangle I want? Or does it only work for some triangles? If you're not sure, read the first sentence. Yeah. Right triangles, that's right, yeah. The Pythagorean theorem is a tool that we can use that tells us the relationship between the three sides in a right triangle. Must be right. Meaning that there's a 90-degree angle in there, okay? So I think someone mentioned the word leg earlier. When you're talking about a right triangle has two legs, which are the two sides that make up the right angle, right? So this side here and this side here would be the two legs of the triangle. Okay? Now, I asked you guys earlier, what is the Pythagorean theorem? You guys said a squared plus b squared equals c squared. Okay? Does it matter, if I were to label this triangle, does it matter which side is A and which side is B and which side is C? Or could I label them however I want? If I said a squared plus b squared equals c squared. Could I put A here, B here, and C here? Does it matter? Yeah. Correct. A and B don't matter, but c squared must be the longest side. Yes. And that has a special name. It starts with an H. Do you guys remember what it's called? Yeah. Correct. It's called the hypotenuse. Okay, so this is A and this is B, or you could switch these around if you want, it doesn't matter. And then we've got the hypotenuse. What I like to do, because a lot of people actually put the c squared in the wrong space in the formula when we're actually working out problems, is I like to change this, and instead of writing a squared plus b squared equals c squared, I like to write it as a squared plus b squared equals h squared. So that I remember that that h stands for hypotenuse, and it has to be isolated by itself, right? That's the square that's by itself. Okay? All right, now let's actually see how we can use this thing. And oh, by the way, do you guys know what it means, a squared? What does that mean? Like, what would 3 squared be? What does it mean to square something? Yeah. Multiply by itself, exactly. So if we're looking at 3 squared, we would go 3 times 3. Okay. So let's actually look at some examples here. Use the Pythagorean theorem to find the lengths of the missing sides of the triangles to the nearest tenth of a unit. Okay, so we're going to start with A. And when we are doing these problems, I want you to start by labeling your triangle. With A, B, and H. And at the very least, label the hypotenuse. Ugh. Hypotenuse. Because one of the biggest mistakes that people make is in using the formula is with where the value for hypotenuse should go. Okay? So for this triangle over here, which of these three sides is the hypotenuse? Yep. Q. Good. So this over here is the hypotenuse. Okay? The other two are A and B, and it doesn't matter which is which. Okay? Now we're going to write out our formula. A squared plus B squared equals H squared. Okay? And fill in what you know. Okay? So do we know A? Yep. And in fact, it doesn't matter which is which, so maybe I'll call this A and this B. Yep, so A, the way that I've labeled it, is 3.8. So I'm going to fill in A is 3.8, so this is 3.8 squared. Plus, do I know B? Yep, that's 5.2. So 5.2 squared equals, do I know H? No. What is the letter that is used in this triangle for H? What's the letter along the hypotenuse? I kind of covered it up on the picture, but you guys should be able to see it in your notes. Q, yeah. So I'm going to call this Q squared. Okay? And then what we're going to do is evaluate the squares and sort of simplify. So what I mean by evaluate is like, what are they equal to? Now, on your calculators, okay, if you want to go 3.8 squared, there's a couple of options. You might see one of three buttons. You might see a button that looks like this. You might see a button that looks like this. Or sometimes it's y to the x instead of x to the y. It's the same thing though. Or you might see a button that looks like this. And in fact, you should see one of these two, one of the last two. You may not see the first one. Okay? So you need to take out your calculators and make sure that you can find that button. Okay? So when you are putting this into your calculator, you're going to enter in 3.8. This is sort of your exponent button. This squared is an exponent. This tells you how many times do I need to multiply 3.8 by itself. Okay? And this little hat button is also an exponent. So your calculator won't have both of these. It'll have one of these two buttons, depending on which type of calculator you have. Okay? So on your calculator, and if you have a square button, you can just write 3.8 and then press the x squared button and it'll square it for you. So you're going to go 3.8 and then hit one of these two. Mine has this one, to the power, and then put 2, and then enter. Okay, now if this is really confusing or if you get stumped later on, what does 3.8 squared mean? Yeah, it's 3.8 times 3.8, right? So worst case scenario, you just go on your calculator, 3.8 times 3.8. Okay, what did you get? Yep, 14.44. Okay, now let's do the same thing with 5.2. What's 5.2 squared? Yep. 27, I think it's 0.04. Is that right? Okay, so that's these two values equals, there's nothing to do on the right side, so this is just still q squared. Okay, and just like we were doing with the proportional reasoning equations, I am lining my equal signs up vertically. Okay, so I can clearly see a left side and a right side. All right, now what could I do on the left side? Add them together, exactly. Okay, so what is 14.44 plus 27.04? Yep. 41.48. And that, there's nothing to do on this side, it's still just q squared. Okay, so I'm almost there. But I don't want q squared, I want q. So now I have to think about opposite operations. Okay. What's the opposite of addition? Subtraction. What's the opposite of multiplication? Division. Okay. Do you guys know what the opposite of squaring something is? If you, for example, let's say you took 5 squared and you got 25, how would you get back to 5? Yeah. But you don't know, when you take 25, you don't know that it's 5. Yeah. Square rooting. Yes. The opposite of squaring is square rooting. The square root of 25 equals 5. So squaring and square rooting are opposite processes. So if we have a square, if we have q squared, and we just want q, we need to take the square root of 41.48. Okay? So you have to look for another button on your calculator that should look like, it should look like this. It'll either look like this, or sometimes there's a little 2 in there. Okay. On some calculators, you have to put the 44.1 or 41.48 in first, and then hit the square root button. And on some calculators, you have to put the square root button in first, and then enter 41.48. So you just have to figure out how your calculator works. Okay? What do you get? What is the square root of 41.48? Did anyone get it? I can pull this out. Oh, here, I have it here because I just did it with the last class. So on my calculator, in fact, for me, I have to press the second function because it's right over here. So I have to go second and then hit that button, and then I can enter in 41.48. Enter. Okay, and rounded to the nearest tenth, that would be 6.4. Okay, so this is 6.4, and I believe, what were the units on that triangle? What were the other lengths? What were the units for the other sides? Were they in like centimeters or what? Yeah, meters. So this is 6.4 meters equals Q. Okay? Right? So once we fill in what we know, the rest over here, what we're doing here actually is we're solving. We're solving the equation. All right, let's do one more. Okay, so here's another triangle. Now, first thing, label the triangle. What's the hypotenuse in this triangle? Yeah. Which one? Is it Z? Is that the longest side? Yes. It's X, yes. And if you're having trouble finding it, it's always the one across from the right angle. Okay? So it's this guy over here. This is the hypotenuse. Okay, so this is a really common error, is that people, when they're especially when you're going quickly, students often, when they're going quickly, think that the hypotenuse is whatever side is unknown. And that's not always true. In fact, it's only true like a third of the time, because there's 3 sides, right? So chances are, only a third of the time, the unknown one is going to be the longest. So you have to be really careful, and that's why I really don't want you to skip this first step. Explicitly label the hypotenuse, because then you prevent the mistake of putting the wrong value in on the right side by itself. Okay? The other 2, it doesn't matter. You can label them A and B. Okay? So if I put in my formula now, a squared plus b squared equals h squared. Okay? On this diagram, a, the way I've labeled it, is z, so we don't know that one. Plus b is 6.9 squared equals, the hypotenuse is 12.8 squared. Okay? All right, what do you think we should do next? Put everything into the formula. What could we do with this? Yep. Yeah, so, oh, just give me one sec. All right, so I think what you were saying was we could subtract the 6.9 squared? Yes, okay. So yeah, we need to get z squared by itself. So there's 2 things that we could do here. We could either figure out what each of these squares is first. We could go 6.9 times 6.9 and 12.8 times 12.8. Or we could subtract 6.9 squared from each side and then figure out what the squares are. So let's go with your suggestion, okay? And the reason is, you guys, is because eventually, if we need to get z by itself, we need to get z squared by itself, okay? Now, if we're adding 6.9 squared to it, we have to undo that so that it's by itself, okay? What's the opposite of addition? Subtraction, yes. So minus 6.9 squared minus 6.9 squared. Okay, so you can subtract the 6.9 squared first if you want. Did anyone think of doing 6.9 times 6.9 first and 12.8 times 12.8 first? No, you all were, oh good, okay, cool. So then what we're going to end up with is all that we have on the left side is z squared, and on the right side we have 12.8 squared minus 6.9 squared. Okay, now what? Now what are we going to do? Subtract them? Okay, so how would you subtract them? Like you'd go 12.8 minus 6.9? What do you think? Think about order of operations here. What types of operations do you have? Remember, order of operations is like this. What do you see here? I see subtraction. What else do you see? Where do you see the multiplication? Yeah, so squaring is like, it is multiplication because it's repeated, we're repeating the multiplication of 12.8 by 2, right? But because we're squaring it, that's like an abbreviation, which is an exponent. Okay? But either way, we have to address the squaring because it's a form of repeated multiplication before we address the subtraction. Okay? So what we need to do is we need to address the squares first. Yeah. Okay? So what is 12? Well, okay, so there's two things you could do here. First, what's 12.8 squared? What is 12.8 squared? 163.84 minus, what's 6.9 squared? Yeah. 47.61, okay? And then when you subtract that, what do you get? $116.23. And then what do you get? Oh, sorry. Then what do we have to do, actually, to get z? We don't have z yet. We have z squared. To get z, what do we need to do? How do we undo squaring? Square root, yes. So z is going to be the square root of 116.23. Yep. 10.78. Okay, so let's maybe round to the nearest tenth. That'd be 10.8, and this was in inches. Okay, now one thing I want to just show you guys is that if you have a scientific calculator, your scientific calculator should be able to do order of operations for you. Okay, so what I'm going to do is I'm going to enter in 12.8 squared minus 6.9 squared on my calculator. Can you see that? That was like this line over here. That was this line right here. This line. That's the 12.8 squared minus 6.9 squared. Okay, and I can do that all on my calculator in one go because just about all scientific calculators can do BEDMAS. And if you hit enter, you get that 116.23 in one shot. Okay, so that can kind of speed things up a little bit. I feel like I'm going to sneeze. Excuse me. Okay. All right. Whoops. There we go. So example 2, I want to discuss it with you briefly, and then I'm going to get you to work on it yourself. Okay? This is one of these situations where we have two triangles that are connected. Okay? So we've got this guy down here, and then we've got one that's sort of sitting on top of it a little bit. Okay? And we're asked to find two side lengths, x and y. Okay. Let's say we wanted to find y. Do we have enough information to find y? Y is this one right here. Could we find y right now? No, why not? You're right, we can't find it right now. Why not? Yeah. Exactly. You need at least two sides to find the third side of a right triangle using Pythagoras, right? So we don't have two sides, we only have one, which is the 10.4, okay? Do we have enough information to find x? Yeah, because we've got these two sides. So we could calculate x. Once we calculate x, would we have enough information to calculate y? Yes. Good. Okay. That's what I want you guys to do. Okay, so I'm going to give you guys about, let's say till 1:30, 8 minutes to do that now. Okay, for homework today, you need to do this. Page 295 to 296, number 2 to 5. Okay, I want you to do some practice on Pythagorean theorem. You're not starting it now, though. We're moving on. That's for you to do at home. Yeah. We're taking advantage of the time that we have here. All right. We're going to start to do a few investigations right now. You might not really know where this is leading, but it's going to lead us towards the trigonometric ratios. That's what they're called, okay? So you're going to kind of have to go with me for a little bit with what I'm going to ask you to do. But what we're kind of building here is we're building some information together so that we can use it to have an understanding of this thing called trigonometry. Okay, so what I'm going to ask you to do on this grid is I'm going to ask you to draw 3 triangles, and we'll start by doing it together. Okay, the first one has a base of 5 and a height of 3. So it's going to look like this. It has to be right. So maybe I'll do the height first. So here's the height of 3. Okay, and a base of 5. 1, 2, 3, 4, 5. Okay, and please be as accurate as possible. You must count squares. And also, try and draw this line as straight as you possibly can. This little exercise is dependent on precision. That's the first one. The second one that I want you to do is going to have a base of 10 and a height of 6. Okay, so maybe I'll do the height again. So height is 6. 1, 2, 3, 4, 5, 6. And base of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let me just double check that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. Okay, and that's a right angle right here. And then again, I'm going to draw a very straight line, and if you have a ruler, even better. Okay, and then the final one has a base of 7.5 units and a height of 4.5. So here what I'll do is I'll start the height like halfway in between 2 squares. And I'm going to go down 1.5, 2.5, 3.5, 4.5. That's a little high, so I should actually cut it off there. And then I'm going to go across 1, 2, 3, 4, 5, 6, 7.5. Okay, and again, please be like as accurate as you possibly can. And there's my third one. So this is 6, this is 10, this is 4.5, this is 7.5. So what I did is I started the height like halfway between a square, and then I went down half, 1.5, 2.5, 3.5, 4.5. And then I went over 7.5. Okay? So you're going to draw those 3 triangles. And then you're going to take out the protractors that I gave you in our last unit. I'm going to make this one a lot smaller. Hold on. I'll do it from here, I think. No. There we go. That's what I wanted to do. Perfect. Okay, you're going to take out your protractors, and you are going to measure something called the angle of elevation, which is this angle down at the bottom, right over here, for all 3 of them. This is why it was really important that you do this accurately and draw your lines as straight as possible. So this angle right here And then you're going to do the same thing for this angle over here. And then you're going to do the same thing for this angle over here. You can see my line is a little wonky. Oh, wait, I got to move it over there. There. Okay? And you're going to just record it, maybe beside or inside the triangle. You can record what that angle is. Yeah, write the angle in once you get it. Oh, like you could write it like right in here. Oh, wait, I didn't want to do that. Just right in here. Like whatever it is, you write it right in here for now. Just write it right there. Yeah, for now. And then we'll talk about the chart underneath in a minute. Okay? Okay. Do you guys need more time? Yeah, a minute more? Okay, one more minute. Okay. All right, what are we getting roughly for this angle in any three of them? Yeah.
So for the smaller triangle, I got 27 degrees.
27, okay. Anyone else? Yep. Did anyone get it? I see everyone with their protractors down, except for maybe one person. So I'm assuming that you're done. So I'm assuming you have an angle measure there. Did you all get 27 degrees? No? Okay, what did you get? 35. Okay, what did other people get? Yep. Yeah. 25. Okay, I want you actually to, I'm going to pause the recording for a sec, because I actually want to come around and I want to check your diagrams. Okay, so I told you guys to count, remember? Really important. So now that we've taken a closer look at this, what are we getting for these angles roughly? What are we getting? What does this one look like to you over here? And I didn't do the greatest job, but what does that look to? Like about 30. Yep, okay. What about this one? Roughly. What does that one look like? $30. Yeah. What does this one look like? Roughly 30 degrees. So they're all the same. Okay? Now, if you didn't draw the triangle with the right dimensions, or if you did something like this, where you drew a triangle and then you went like this, whoop, and you kind of made it a little curved, like this, and didn't draw it straight, that's really going to affect your angle. So that's why I said make sure you're doing it with a lot of precision. Okay, now another thing that I just want to point out to you guys, because I don't know if I emphasized this. I know I touched on it once, but I don't know if I emphasized it when we talked about parallel lines, is that we know what all three angles in a triangle add up to. Does anyone remember what that sum is? The sum of all three angles in a triangle? How many degrees is it? It's not 90, because this one down here is 90, and you have to add another 2. But let's look at a square. Let's start with this. Let's suppose we have a square. What's the angle measure of each angle in a square? 90. Okay, and how many of them do we have? 4. Now, if I split an angle, a square rather, in half, what do I get? Oh yeah, sorry, that's a good one. So 4 angles in a square add up to 360 degrees. If I split that in half, I get 2 triangles. What do the angles in each of those triangles have to add up to? 180, exactly. It's got to be half of what they would add up to in a square. Yeah. So if these are each about 30-ish, and these are each 90, could you figure out what this one would be? The 3 of them all together have to add up to 180. So could you figure out what the third one would have to be? How many degrees are already accounted for here? I've got 90 degrees and 30 degrees. What is that so far? 120. Okay. They have to add up to 90. What's left over? 60. Yes. So to get this angle, we can go 180 minus 90 minus 30. We can take away the other 2, which is 60 degrees. Okay, is that going to be the same for the other 2? Yeah, because we're subtracting the same thing. So these are also both 60. Okay, so these angles are the same in all 3 triangles. Think about what we did earlier this week. What does that mean about these 3 shapes? What did we talk about yesterday and the day before? Yeah, they're similar. Exactly. They've got the same angles, but they're different sizes. They are similar. These are similar. Okay, now let's do a little bit more analysis over here. Okay, so this angle of elevation, that's the one that we measured. And let's keep in mind that this was not super accurate. So we may be off by like a degree or so, but it's about 30 degrees-ish for all 3 of them. Okay, now what I want to just record is, let's record the length of the base and the height for each of them. And those were things that I just gave you, right? You didn't make those up. The first one, the length of the base was 5 and the height was 3. The second one, the length of the base was 10 and the height was 6. And the third one, the length of the base was 7.5 and the height was 4.5. Okay, now what I'd like to do is for all 3 of them, let's look at the ratio of height to base. Okay, so for the first one, height over base is 3/5. What would that be as a decimal? Take your calculators out. How do you get 3/5 into a decimal? Yeah. What does a fraction mean? What math operation is a fraction? Yeah, division. So you just go 3 divided by 5. What do you get? There you go. Okay. For the second one, height to base, 6/10. What do you get as a decimal? 0.6. And for the third one, height to base is 4.5/7.5, which is also 0.6. Okay? Now this shouldn't be surprising because we're looking at ratios of corresponding sides within the triangles. They're similar. The ratios should be equal. Okay? So what do we notice? Well, the angles are equal. Ratios are equal. But again, not surprising. Because we have similar triangles here, right? And similar triangles, similar figures anyway, angles are all the same, but they're scaled down or scaled up. So the sides are going to be proportional. So if we look at ratios of base to height in all three of them, we're going to get an equal proportion. Okay? All right. So that's the first thing I want to look at. Next thing. Okay, and we're going to look at this triangle here, and there's actually a whole bunch of triangles that are sort of embedded in one another. So we've got this really big one, AHJ, and then within it, we've got all of these smaller ones that are embedded inside. Okay, so a couple of things that I want to notice. Firstly, these angles down here are all right. They're all 90 degrees. Secondly, they all have one common angle, which is this angle here. Angle A is common to all of them. Okay, so if they all have a 90-degree angle and angle A that's in common, what does that mean about these angles at the top? What could we say about those angles at the top? Let's suppose this was 90 and this angle down at the bottom was 40. All of the angles have to add up to 180. So 90 plus 40 is what? 130. Okay, we got to get to 180. How much is left? 50. Is that going to be true for this triangle? That it has to be 50? 40, 90, does that have to be 50? Yeah. 40, 90, does that have to be 50? Yeah. 40, 90, does that have to be 50? Yeah. 40, 90, does that have to be 50? Yeah. So it actually doesn't matter what angle A is. The fact that they have two angles in common means they must have the third one in common as well, because the angles all have to add up to 180. Okay? So angle A is common to all of the triangles. How are all of the other angles related? Well, top angles are equal. And that's because they are all 180 minus 90 minus whatever angle A is. I gave the example of 40 degrees, but we don't know what it is. Okay.
Please excuse this interruption. If you are the owner of a white Ford license plate NXU331, could you please go and move your vehicle? You're blocking the dumpster.
Okay, what does that mean about all of these triangles if all of their angles are equal? They're similar. Okay, so I'm going to leave it there for today because we're about to run out of time. I think what I'd like you to do, though, maybe we could just start to do this, okay? Start to fill out some of the side lengths here. So for triangle ABC, let's just look at the small one, and then we could start with this tomorrow, okay? For triangle ABC, if you look at the hypotenuse, that's the little guy, okay? The hypotenuse there is 5. It's the longest side. Okay, so I'm going to put in a 5 here. The side opposite angle A, opposite is like across from. Don't pack up yet. That's 3. So that's the side opposite. The side adjacent. Adjacent means next to or beside. So the side adjacent is 4. Okay? If I look at triangle ADE, that's this next one, ADE. How long is the hypotenuse? From here to here, from A to D. How long is that? From A to D. Yep, 10, because it's 5 plus 5. So I'm going to put a 10 in there. How long is the side opposite? This one? 6, right? It's right here. And what about the side adjacent, next to A to E? 8, yeah. So here's what I want you guys to do for tomorrow. I want you to fill out the next 2 rows of just this part, okay? You can do that in the last minute before the bell, okay? And also, don't forget about the Pythagoras homework on page 295.